We continue our discussion on Deep Learning Toolkit. In this talk, let us build and use deep learning models. To do this, we will explore PyTorch and Timm. By this time, we are already familiar with our development environment and numerical libraries. We will now introduce a widely used deep learning framework called PyTorch. We will also cover a popular PyTorch library called Timm. Timm implements many of the state-of-the-art deep learning models and algorithms so that we do not need to build them from scratch. PyTorch is a popular deep learning framework based on Torch. It has similarities to NumPy data structure and strong support for GPU. PyTorch is used by technology companies. Listing here are the references that are good starting point for learning about PyTorch. There are four main reasons why PyTorch is the choice of deep learning framework for this course. First, it is easy to build, train, validate, and debug models. This is important for beginners, intermediate, and advanced users. Second, state-of-the-art models are available. Both open source model implementations and pre-trained weights are readily accessible. Third, huge community of users means help is available. Majority of recently published papers also use PyTorch. Lastly, it is production ready. Many technology companies deploy trained models built using PyTorch. To install PyTorch, run pip install TorchVision TorchAudio. Then do a simple test. Our objective in this discussion is to build a working model that we can already use. Therefore, we will focus on two items: Torch Tensor as PyTorch data structure and model inference in PyTorch. We will learn more about PyTorch in our future discussions. For the meantime, these two items are sufficient to enable us build a working deep learning model. Let us focus on Torch Tensor, or simply Tensor. In PyTorch, input data, model parameters, and output data are all represented in terms of tensor. Learning tensor is easier if we have good background in NumPy arrays. In NumPy, our basic data structure is called array or ND array. ND array is a multidimensional tensor. For PyTorch, the basic data structure is called tensor. By the name itself, it is multidimensional. In this example, we show the data structure class name by calling type. In PyTorch, input and output data are represented by tensor. Model parameters are also represented in tensor. All important computations like inference, gradients, and loss are expressed in terms of tensor. In terms of hardware support, ND array is limited to CPU, while tensor runs on both CPU and AI accelerators like NVIDIA GPU, Google TPU, and GraphCore IPU. This means even if you have AI accelerator on your machine, NumPy cannot take advantage of that. All tensor computations are still slow because they are executed in CPU. Like NumPy, common tensor operations like initialization, multiplication are supported. In this example, we initialize two tensors, A with size 2 by 2 and X with size 2 by 1. We demonstrate multiplication using Python at PyTorch matmul and einsum. Tensor attributes like size, shape, and data type are shown. Unlike NumPy, PyTorch supports AI accelerators like GPU. We can determine if GPU is available by running Torch CUDA is available. In most laptops, CUDA will not show up and only CPU will be indicated. In GPU servers, CUDA should be available to PyTorch. Let us create TensorA. By default, TensorA is in CPU even if AI accelerators are available. In PyTorch, we have to explicitly tell that TensorA must be loaded in GPU by calling the to method of TensorA. After calling to device, Tensor is now in GPU 0. In this server, there are multiple GPUs on board. Let us examine TensorA again. We can see the device is different when Tensor is in GPU. What if we want to pull the tensor back to CPU? We can call the CPU method. In our discussion about NumPy, we learned that it is used to load data from the file system. How do we pass this data to PyTorch? And after PyTorch has processed this data, how do we transfer the results back to NumPy? In this slide, we demonstrate this scenario. In addition, at every step, we also show in which device the data is processed. It is either at CPU or GPU. We assume that we have a GPU-enabled machine. In the first line, we initialize TensorA with size 2 by 2 with constant values. Next, we convert this variable to a PyTorch variable. Afterward, we send the TensorA to the GPU by calling CUDA method. It's another way of passing CPU data to GPU. Next, we send the tensor back to CPU by calling CPU method. And then lastly, we return the data back to NumPy. Model inference is probably the most practical part of the discussion so far. In this section, we will build an image classifier. The conceptual framework of an AI model is made of 3 parts: input data, a trained model that ingests the input and makes a useful output prediction. For example, in this case, we have a trained classifier model that accepts an input image and correctly predicts that it is a cat. We will closely examine these 3 components in PyTorch and demonstrate a practical working model. The input is any type of data. It can be image or video. It can be speech or music. It can be 3D like point cloud. It can be text like character, word, or phoneme. There are many forms of data that exist. For example, this is protein structure, which is used in the field of computational biology. Before an image can be processed by a trained model, it must be in a proper form. Let's load an image using PIL. In the past, we used matplotlib to load images. In this example, we use PIL so that we can directly use PyTorch to transform it to a tensor. When dealing with data, it's always a good practice to visualize it. This enables us to have a better understanding of what we are processing. It is also a good way to debug our deep learning pipelines. Loading text as input data requires some hack. Since models understand numbers only, text must be converted into numerical format. One commonly used method is to index a word. The integer index represents the word. For example, in this case, 0 is hello and 1 is world. Then we use torch embedding to convert this integer number into a vector. Why do we have to use word embedding? Embedding enables us to project words into a multidimensional space. Words that are closer in meaning, like king and queen and Paris and Tokyo, will be near each other. Therefore, embedding incorporates a form of semantics into our input text data. 1D data such as speech and audio can be loaded by using Librosa. In this example, we load speech data in WAV format. The important information like waveform samples and sampling rate are extracted by the load method. Similar to vision, it's also important that we visualize the audio data. We can also listen to it to validate the content. It is best to mention that PyTorch has extension libraries for audio and video. TorchVision enables us to access popular vision models like COCO for object detection and segmentation, and kinetics for video action recognition. TorchVision has model architectures like ResNet or MobileNet so that we don't have to build and train them from scratch. TorchVision has image and video processing functions such as resize or crop that we will use later. There is also TorchAudio. It provides APIs that we can use to load popular datasets, models, and implementation of signal processing functions such as MEL spectrogram from audio signal. There are other PyTorch extensions such as TorchText for NLP and TorchRec for recommendation systems. Like Pill, we can use TorchVision to load images from the file system. In this example, we use IO read image. Note that Jupyter display understands Pill images only. Therefore, we have to convert the image from Torch tensor to Pill before calling display. TorchAudio can also load audio data like Librosa. This is the implementation using TorchAudio. TorchVision enables us to build and initialize state-of-the-art models using pre-trained weights. In this example, we construct a ResNet 18 model and initialize it with weights from a previously trained ResNet 18 on ImageNet 1K. This ResNet model is ready to be used for inferencing. There is a long list of models that are available for use in TorchVision. Please visit this link. We have loaded both the data and the model. Before doing prediction, there are certain housekeeping tasks to be done. Let us focus on vision data and models. First, ensure that the data is in PyTorch tensor format and in the range of 0 to 1. This can be done by calling toTensor method. Better yet, resize and normalize it such that it is more suitable for prediction. This is an improved transform method which is composed of resize, crop, toTensor, and normalize. The sequence must be done in proper order. After the series of transforms, the original image now looks like this. Because real-world images are inherently different, normalization is a way to minimize the variations to help the model in its prediction. We are now at the last stage, which is prediction. Like input data preparation, there are certain housekeeping tasks to be done, such as switching the model to evaluate mode to ensure that dropout layers are disabled. Ensuring that the input tensor has a batch dimension. Note that models can do parallel prediction. In this case, since we only have one image, we reshape the input tensor to have batch size of 1. The next part is the actual model inference. In this case, we enclose the prediction in a no-grad context to ensure that no gradients are computed since we are not training the model. Last part is extracting the index of the label or class with the highest probability. This is through Arcmaps. What is Arcmaps? Note that the outputs of the model prediction are probabilities. In this case, 1,000 probabilities stored in the TensorPred. Arcmaps examines each element of TensorPred until it finds the index with the maximum value. In this case, that would be 285. Note that in this scenario, the model prediction did not use softmax to convert the last layer's output to probabilities. Essentially, we have unnormalized probabilities. Nevertheless, the output of Arcmaps will be the same, and that's what matters in the class prediction. While index 285 makes sense to the model, it does not make sense to the human end user. We want to know the class or label. In this case, we have to use a lookup table that stores the conversion from index to human readable object label. This is the actual list of labels for ImageNet 1K objects. For 0, that would be tench, 1 for goldfish, and so forth, up to index 999, which is toilet paper. So what is the label corresponding to 285? That would be Egyptian cat. According to ResNet 18, our cat image is an image of an Egyptian cat. The pace of development of deep learning is fast. Even for PyTorch with hundreds of contributors, it is hard to catch up. Timm is an open source project by Ross Whiteman that has been very useful to the PyTorch community. Why Timm? From the documentation. In short, Timm provides many important and state-of-the-art algorithms and models that are not found in PyTorch libraries. For example, label smoothing for regularization, exponential moving average of parameters during training, and EfficientNet version 2 models. Installing and using Timm is easy. Install it through pip, then use it using Timm's create model method. In this case, we created the same ResNet 18 using Timm. Please note that the weights will be different, but the performance scores of the two models should be close. In the next part, we will have code demo. The details of code examples can be found in GitHub. In this demo, we will use a pre-trained model to perform inference on a single image. There are three components to this demo: the input, the model, and the output. We'll cover these components in detail below. Let us first import the required packages. We use a pre-trained ResNet 18 for inference. The model is available from TorchVision or from Timm. When we use a model for inference, we need to specify the eval mode. This is because the model is in train mode by default, and we need to disable all the dropout layers. This output shows the model architecture of ResNet 18. For the input, we can use matplotlib image to load an image into a NumPy array. However, PyTorch transforms expects a pill image. While we can convert NumPy array to pill, we can load an image directly into a pill image. This is loading of the image using pill, and then this is displaying the image on the screen. These are the transforms that we discussed, and this will be the resulting image after transform. Let's run this code and enter the image from the file system. This is the image and some information about the image tensor like torch flow 32 and the shape. Let us now focus on the output. We will use the image tensor as input to the pre-trained ResNet 18 model. But before running the model for prediction, there are two things that we should do. First, include a batch dimension. In this case, we will use a single image. So we need to add a batch size of 1. This is done through rearrange. Next, we execute inference within Torch no-grad context. This is because we don't want to track the gradients. The expected output is a torch tensor of shape 1 by 1000. This is because Resident 18 was pre-trained on ImageNet 1K. We can then use Torch Arcmaps to get the index of maximum value. Let's execute the code. And this is the index of the highest value. That's 285. To make sense of this predicted index, we need to convert it to label. So we will use the lookup table as presented in the slides. This can also be downloaded from this link. Let us execute this code, and we can see that using the lookup table, 285 is actually an Egyptian cat. The next demonstration shows how to use TorchVision and TorchAudio to load and visualize input data. Let us first load all the necessary Python modules. The first data that we will load is image. This is done through TorchVision IO read image. The file name of the image to be loaded is shown here. After loading, we will convert it into PIL so that we can visualize it on the screen. Let us run this code. This is actually an image of a bird. The next thing that we will do is to visualize this same image after undergoing a series of transform procedure. These transforms are resize, center crop, normalize, and then we will display it on the screen. Let's run this code. This is actually the image of bird after undergoing a series of transforms. Let's do another experiment. What if we remove the normalize by commenting it out? Let's run the same code, and we will see that is actually the version of the image with only resize and center crop applied. The last part will demonstrate how to load speech data from the file system and how to visualize it. First, let us define the function plot waveform. This is actually a function from TorchAudio. Then we will use the TorchAudio to load the speech data, and this is the path to the speech data. We can visualize some metadata by using TorchAudio info. The actual loading is done here. It outputs the WAV and the sample rate, which we can display and listen to. We can also use the plot waveform we earlier defined in order to visualize it. Let us run this code. And lastly, this one. We can see here the metadata about this speech WAV file. We can listen.
The association was organized under the most promising auspices.
And we can see the waveform as plotted here.